Welcome this morning to the JUCE Summit, and welcoming to Developing Audio Apps with JUCE. Will be hosted by Timur and by me. We're both JUCE developers in the JUCE team. Yeah. And I'll do the first part. I will be talking about some of the APIs and classes that are already in JUCE, and some minor new features, and Timur will be talking about some of the major new features in JUCE. Okay. So let's get started. So you are all, should all be very proud to be in this room. Because if you're in this room, this means you are a C++ audio developer. And that's probably one of the hardest things you can be. Because if you're writing audio code, if you're writing any kind of DSP code, you all know it has to be fast, it has to be optimized, you'll have to write in some kind of compiled language, let's say C++. It needs to be optimized code, it has to be real-time hard, no locks in your audio thread, please. If you're doing DSP, you'll be doing complex DSP algorithms. You might be doing Fourier transforms, Z transforms, you name it. But at the end of the day, when you have everything done and everything written, you're going to have to listen to your plugin. You're going to, there's a bit of creativity in there as well. You're going to see how does it sound, how does it feel, is the synth, does it have enough bass? And yeah, it's very, very, very challenging to do. So all of these things are incredibly hard. So this is what you really, really do best. You excel at writing audio apps. And the world would be great if that would be the only thing. But unfortunately, we have these guys here. We have getting audio and MIDI into your app and back out. Can't be too hard, right? I mean, let's see. So on Mac, yeah, we use Core Audio. Everything's good, right? That was a day, maybe a week of programming. Okay, wait, Windows, there's 3. Well, actually 4, because MIDI, there's also this direct music. And then, I mean, it's not only Mac and Windows, right? So we have iOS, Android. And then we have all these plugin formats. Yeah, the DAWs want to talk through plugins, and it's 4 different types. And well, if you want your app to be running on all these platforms, obviously you want user interface, you want 2D, you might want 3D, you might want to do some copy protection over the network. You get the picture. Your audio app is very, very small on that slide. And there's this big territory of mess and madness. And well, at JUCE, we try to abstract that away. We try to hide this from you. And we try to wrap everything in beautiful and neatly packed classes. So that at the end of the day, you can focus on this. So that's what JUCE, the goal of JUCE is. Okay, talking about these neatly tidied up classes that hide all this mess away, this is what this talk is going to be about. It's going to be about an overview of the JUCE audio classes, only some of them. There's so many, and I can't go into detail of all of them. And we'll be talking about some of the new JUCE 4 classes. So let's start with the most important class, which is the Audio Device Manager. The Audio Device Manager is especially important if you're writing your own standalone application. And the Audio Device Manager handles all of the devices. You can open and close MIDI and audio devices. It's an easy way to store and load device settings. So if you close your application and open it again, you can easily get the last audio device that was open. It talks to your app via callbacks. So the Audio Device Manager sends callbacks to your app, asking for more audio and giving you more audio and giving you more MIDI. And you see the orange line is the flow of audio, and the green line is the flow of MIDI with the Audio Device Manager. So this would be a typical audio app. I'm deriving here from Audio I/O Device Callback, because I'll be implementing these 3 methods here: Audio Device I/O Callback, Audio Device About to Start, and Audio Device Stopped. So I have to fill them in with something. And the Audio Device Manager is just a simple member variable here on the stack. And it's default constructible, so it doesn't take any arguments when you construct it. But we need to initialize it with something. So let's do initialize with default devices. The first parameter is the number of input devices. I'm going to take 0 here, and then the number of output devices will be 1. There are other methods to initialize the device manager, like loading your last setting, and there's more ways to initialize this. I'm also going to ask the device manager to give me audio callback. So I'm going to say add audio callback, this. And here in the audio device about to start, when I call initialize with default devices, in turn the device manager will call audio device about to start and give me which device it actually chose for the audio, and then I can probe it. So here I'm going to say sample rate equals device get current sample rate. And here I'm just going to fill this out with some audio. So I'm going to make a little for loop here. Output channel data. Output channel data is a pointer-pointer. The first index is the channel. Because I only have mono, I'm just going to do 0 here. The second is the actual sample. And let's just play a sine wave. So divided by the rate, and should be, if I don't have any typo, is the sound on? Yes. Then we should be hearing something now. Sorry? Thank you. That's it. Oh, turn it down, please. It's going to be loud. There we go. So here. So this is the smallest audio app you can probably come up with, and a very annoying one. So let's just maybe turn down the. There we go. Okay. So this is like a little diagram of this little audio app. We have the audio device manager sending us callbacks, sending us audio. Our audio app does something with the audio. I didn't do anything in my case. I just ignored it. And I produced audio, which goes back to the audio device manager and then goes to the output. So the audio device manager, making an app like this is really only useful for very, very simple apps where you don't have any complex graph. You don't have to present yourself as a plugin. You don't want to load any plugins. Then this is what you do. Okay, one of the most useful classes in JUCE is called AudioSource. And I use this one a lot. And I think you can do a lot of complex things with this little class here. So an audio source is something that only produces audio. So it doesn't have any MIDI. It doesn't have any audio input. It just produces audio. And you can see here the methods that an audio source must support. Again, it has this prepare to play method. It has release resources. And the most important one is get next audio block. So you're constantly probing the audio source for more audio. And this get next audio block takes us a bit peculiar parameter, which is just a buffer and the start sample and the num samples within the buffer. So again, here I have my little audio app. I have a JUCE audio source called Tone Generator Audio Source. I initialize my device manager. I tell the device manager I want to receive callbacks. Now here in the audio about to start, I'm going to have to tell my source that it should prepare to play. So prepare to play takes 2 parameters. The first one is the estimated buffer size that my audio device has. So I'm going to probe the device here, get current buffer size samples. And the next parameter is the sample rate. So get current sample rate. Here on audio device stop, we do source release resources. And here we are going to wrap the parameters that come in, these raw parameters, into an audio sample buffer. So just use a construct of audio sample buffer. The first one takes a double pointer. The second one is the num output channels, or the number of channels. And the third one is num samples. and the audio sample buffer does not copy the data, it just refers to that pointer. And now we can pass this to our source. We do get next audio block. This bit strange guy called AudioSource channel info, which has a nice useful constructor where you can just give it a buffer. So do this, and if I haven't done any mistakes, here we go. It's just passing on the sound that this tone generator audio source is producing and just passing it to the device manager. Please stop me, by the way, if you have any questions. Yeah. Okay, so that was a bit tedious. We just wanted to have an audio source. We just wanted to get it out. So there's a very useful class called AudioSource Player. And the AudioSource Player acts as a bridge between the audio device manager and audio source. So I'm just going to add this to this app here, AudioSource Player, and I'm going to tell the player that the source is source. Just have my cheat sheet ready. Then I'm in the deconstructor, I'm going to. So what I now, if you notice that the class does not derive from audio I/O callback anymore. So my app is not expecting callbacks from the device manager. I'm just going to pass it on to the audio source player, which then does everything for me and passes this then on to the audio source. So this is why I'm going to tell the device manager that when my audio app tears down, it should remove the audio callback from the player. And here, likewise, I want to tell the device manager to add the audio callback. So if I haven't done any mistake, which it seems I have, yeah, because we don't have a source yet. Should probably do the right order. There we go. Yep. So this simplifies this a lot. We don't have any callbacks anymore. The audio source player takes care of this all. So what other audio sources are there in JUCE? There's a very, very useful one called the audio format reader source, which will just take an audio format reader here from the format manager. I do create reader for a file, and I can pass this to this audio format reader source and just attach that to the player. So here we go. That's the audio format reader source. But a really useful thing about these audio sources is that many of the JUCE audio sources can in turn take another audio source as an input. So although an audio source as such, the base class, can only generate audio, the individual subclasses, the individual implementations of audio sources can, if they want to, take another audio source as its input. So you can create chains. So this is what I'm doing here. I factored out this create file source where I create an audio format reader source, which reads the file. And then up here, I create a reverb audio source, which as a source itself uses the file source. So. But this can get even more complex because there's another nice little JUCE audio class, which is called mixer audio source. And here we can create it and then just do add input source, add input source. So in these few lines of code here, I'm creating this complex graph. I have a audio format reader, so it's reading some audio file. It's adding a reverb to it, and that's mixing it with some other song. So horrible. I really see AudioSource as a big alternative to AudioGraph. I see a lot on the forum, people like, oh, I want to use an AudioGraph, that's so amazing. Actually, chaining audio sources is a lot more lightweight. And if you don't need any graph theory stuff, so you don't need any like analyzing if there are any loops in your graphs, and if you're okay with constructing the graph manually, and you don't need any audio processors, such as any third-party plugins or something, then just chaining audio sources and mixing them is a really, really simple way, and it's a lot faster to write the code. One thing you have to watch out, though, is that the audio sources, they don't own the sources. So you have to also watch out on the order that you delete them so that nothing's using it. But it's just quite simple rules you can follow. So AudioSource is really a very, very minimum interface for producing audio. The AudioSource player simplifies the integration with audio device I/O callbacks and audio sources. And yeah, as I just said, you can create complex processing pipelines by just chaining audio sources. So the next part of this session is are there any questions so far?
Is there example code for all this on the USB you can give us?
I'll send around the slides. That specific sample code is not on there. I'm thinking if there's a good, do you know any good sample for the audio source? So for the audio processor, there's a lot of sample code.
There's stuff in the JUCE demo.
There's stuff in the JUCE demo, yeah, I think so.
We could probably upload some more specific examples.
Right. We will, yeah. Yes?
Does the audio file source spawn a sample code to read the file?
No, good question. So for the video, the first question was, is there any sample code for this? The second question that just came, does the audio file format reader actually run on a different thread? And it doesn't. Very, very good question. I have in my notes that I wanted to ask the audience what is wrong with that code. And it's very, very bad because you don't actually, the audio file format reader will really read it directly from the callback, which is always a bad idea to do on your audio thread. But there's a very simple class which is called audio buffered source or something, which can take any other source, but it will sort of buffer the input source on a different thread. So, and all you would have to do is wrap that audio file source reader. You would just have to wrap that in one of those audio buffered sources. So that would have been a few more characters in my code, but yeah, nicely spotted. Yeah, very, very good. Any other questions so far? Also on the audio device manager. Okay, so let's move on to the heavyweights of JUCE, the AudioProcessor class, and some associated classes. So the AudioProcessor is a heavyweight class which can have audio input, audio output, MIDI input, MIDI output, and can have effect parameters. Unlike the audio source where you just always do get next audio block, the audio processor, the main method is process block, which takes a buffer, an audio buffer and a MIDI buffer, and the audio buffer already comes in containing audio, let's say from your microphone, or I don't know if it's a plugin in a DAW, it will get whatever in the track, and you just apply your effects to that buffer. And the same thing with MIDI. I mean, normally you would only read MIDI, but technically you can also change the MIDI if your effect has MIDI output. So, and because this can be loaded into a DAW, for example, the audio processor also supports having a state. So you can load the audio processor state and save it again. So it has to support this. And last but not least, it can have its own associated GUI, an editor. So an audio processor can support like a little window with, well, you all know it from plugins. Here, I just want to show you how to use an audio processor. And again, I don't want to, like I did with the first step from the audio source where I showed you exactly how to hook it up if you do it manually. I'm not going to do that here. I'm going to use, very similar to the audio source player, I'm going to use the audio processor player, which just takes an audio processor and deals with all the callbacks. So this is going to be very, very similar code. I'm going to add the audio processor player here. Just put it on the stack. Then I'll tell the player that which processor to use. I'm going to use AudioProcessor. So also the players never take ownership. So you can see that I'm just doing an ampersand here. That's fine. Because they never take ownership. And as long as the player is destructed before the audio processor, which in this case it isn't, so I'd have to switch that around, everything will be fine. Okay, so here I then tell the device manager where it should send its callbacks to. And then I need to destruct it. We already hear it coming through. That's fine. Just for completeness. Okay. So that's how to use only the audio part of the processor. So let's just put something there that it stops the music. So we only looked here at this orange path. We only looked at the audio part. And now I'm going to add the MIDI part. So it's very, very similar. I'm just going to tell the device manager that we now also want to have MIDI callbacks. So there, I just do add MIDI input callback. The first parameter is a sort of a filter where I can say from which devices I want to receive callbacks. And if you just give it an empty string, it will just use all devices. And similar as with initialize with default devices, I have to sort of enable the MIDI devices I want to use. So I'll do set MIDI input enabled. And I'm going to tell it to enable the keyboard rise, which I have here. True. And for completeness, again, I should be removing again, I takes a filter and a player. Okay. Now, I think my singing here actually, this is actually me singing. I sampled myself. My singing there is very, very beautiful. And I think the music is a bit too loud in proportion. You all agree, right? And so I'm going to now look at the third part of the here, the third channel, which is the parameter channel, this gray channel. So what I'm going to do is I'm going to look for a parameter called music gain, and I'm going to pull it down a bit. As the parameters are dynamic, the host has to like probe what parameters are there. It has to be able to see what units they are and the range of the parameters. There's not like a single variable I can set. I have to sort of probe the audio processor which parameters it has and then change the correct one. So I'm going to write a for loop now that just iterates through all the parameters and looks for the parameter for the one I want to change. So I'm going to use some C++11 here, just because I can. So that's a range-based for loop. And just double checking that I'm not getting a null pointer back. Then I get the name of the parameter. The 255 is the maximum name length that should return. Some DAWs need that. So, and I'm going to look for a parameter called music gain, and I'm just going to say, hey, you know, music is way too loud. Let's pull this down a bit. So if I didn't do any mistake, which seems I did. Does anybody? Sorry? Ah, very nice. That could have taken me a long time. Yeah, there we go. Yeah, that's a lot better. Okay, so that's how you do parameters. So this was now using an audio processor that was already there, using the audio processor player, which communicates to the audio processor audio, MIDI, and parameters, and the audio processor takes the callbacks from the audio device manager and passes them on. But you might, and just as a note, an audio processor doesn't have to be that processor that I implemented. There are many audio processors already in JUCE, but you can also load a plugin very, very easily. So you can, with 2-3 lines of code, we could also just have loaded a VST or a VST3 plugin in the previous slide. But you might also want to make your own plugin, which is very useful if you want to, you might want to implement your own audio processor, which is very useful if you want to make your own plugin. But also if you want to use the audio graph and you have your custom graph nodes, then you would also want to make your own audio processor. So let's see how that's done. Now, the audio processor has all of these pure virtual methods, and they're quite a lot. And the reason why it's so many is because part of an audio processor, I said before, is parameters, audio MIDI, but also some kind of metadata, the state. And so you have all of these things like get name, you have get input channel name, you have accepts MIDI, produces MIDI. So you have all of this metadata, programs that it can have. So all of these classes need to be overridden, which is a tedious task. But we have the introducer to your rescue. And there, if you just select audio plugin, if you make a new project and select audio plugin, then we have this all in a GUI. So you can, all of these little, all the metadata functions, which is like 90% of those methods before, you can, in the GUI, edit, right? So here you have like the plugin manufacturer, the name, does it produce MIDI, does it want MIDI, is it a synth, et cetera, et cetera. So you can all edit that in the introducer and save it. And this is what I did now. I just took the introducer, I edited a few variables there in name and manufacturer, and I just called my processor JUCE default processor. I didn't change any code in there, right? And I'm just deriving from that. So I have all of these tedious metadata methods. I've got them all covered, and I can focus on the meat of the audio processor, which is here the audio processing code. So I'm just going to add some code here to get some audio out of my my processor. So everything's already there. You can see that when the prepare to play method gets called, I query the sample rate. I reset the position. Here I should actually init the position as well. I reset the position to 0 if we release resources. And here I can now just write a loop over all channels. Buffer get num channels. There we go. And I'm going to get a raw pointer on the channel data, which I can just do with buffer get write pointer, and I give it a channel number. And now I can start writing into the buffer. Buffer get num samples. And we'll do something very similar as we did before. I'm just going to create a sine wave. Let's tune down the frequency from the start so we don't kill our ears. Here, this pause variable is basically just the time, and I have to divide all of this by the sample rate. And fingers crossed, yeah, there we go. So this is a very, very simple audio processor just generating audio. But what if we want to add parameters? And this is, let me just put an at there again. There was an old way how you did parameters in JUCE with, you would override a set parameter value. And the set parameter value would be called by the DAW or by whoever is using the audio processor. There's a new way to do it in JUCE, and I really, really recommend looking at this, and I'm going to show you how, because it's so easy. It's so much easier than overriding the set parameter function. So what I'm going to do is I'm going to create a gain audio parameter. And because the gain is going to be a float, I'm going to use this new class. Well, it's been introduced in JUCE 3.2, I think, audio parameter float. I'm just going to call this gain param. So I'm going to add that parameter by just calling add parameter. And here I can create the parameter. And this is where I now give the parameter a name and an ID. So it takes a string ID, I'm going to call it gain. It takes a name which is presented to the user. This is useful for translation. So the ID is sort of what's stored when you do automation. The second parameter is what's displayed to the user. So you could technically translate it to your native language then. Then is the minimum value, the maximum value, and the default value. And notice that I'm calling new straight here. I'm not I'm not deleting it anywhere. This is because when you call add parameter, the processor, the subclass will own the parameter, and you don't have to take care of memory management anymore. And it's really, really easy to then get the value. So I'm just going to do float, gain, and all you do is star gain param. So this is how I read the parameter gain. And you can see down there that the slides, I have picked up that there's this parameter now. And yeah, there we go. Just for the heck of it, let's add another parameter. So parameter float, which will be the frequency. And watch it appear now below once here the subclass knows about this parameter. So this is frequency. I'm just also going to make this guy go from 1, 0 to 1 because I don't want to deal with sample rates. So I did everything right. You see that it appeared here now. And here I'm just going to do float frac equals frac param. So I just load the frequency. I'm going to times it by the rate just to get it into a nice range and divide it by 10, let's say, just to get it in a good range. But now so this should work. We're not using it. That'd be useful. So here, yeah. Now, as you see here, if you look at the code, we're timesing it by rate, and then we're dividing by rate again here. So let's just put all of this, all of these constants just right back here, and then we can take away the rate, just to clean up the code a bit. So now we have a nice, yeah, there we go. Yep. So that's how you do parameters in AudioProcessor. It's really, really very, very simple. I mean, this is what creates the parameters. This is how you read it. Okay. So, yes?
Is there a way to get the previous value of the... Would you mind repeating your question in the microphone? Sorry, yeah.
Yeah.
Let's try it.
Hi.
Does it work? Switch it. Hello. Should be on right.
Yeah, I'll repeat the question for now. Yeah, exactly. Yeah.
Is there a way to get the previous value of the parameter? So because now you have the stepping.
Yes. So there's something called linear smooth value in JUCE.
Right.
And linear smooth value, you can just wrap your parameter in linear smooth value, and it will smooth out the changes.
Right.
Because obviously, so the question was, can we somehow get the previous value of the parameter to stop this clicking as you hear? You can hear this awful clicking, or if I do this. Oh no, there it's okay, but. And the way you would do it is you would smooth out the parameter changes, and there's a class for that. And Timur.
Yeah, if you want to know more about linear smooth value, you can come to my talk tomorrow.
Okay.
Shameless advertisement right there. Yeah, so that would be the solution. If you would want to do it yourself, there's like no way in JUCE to get the previous parameter value. You would have to have like a ring buffer. You would have to store it somewhere. Yeah. Okay, so that was that. Okay, so where are we? Yep. Okay. So yeah, that's the audio processor part. Is there any questions about audio processors? This was a very, very brief overview. There's so much more to talk about audio processors, but is there any other questions on audio processors? Yes.
On this question, we generated our own signal.
Yeah.
What about changing signal which comes from outside?
Yes. So that's a good question. So the question was, here we just generated, oh, that was wrong. Here we just generated our own signal to go, so was it here? No, where is it? Sorry.
Actually, still it's not a processor, it's a generator.
Right. So here we just generated audio, and the problem is that I didn't want to do anything that needed a microphone here because I didn't know how the feedback would be. But this buffer comes pre-filled in with audio coming in, and I just overwrote that. But I'm not going to do it here because it's probably going to do like massive loopback, but I could just take buffer and just times it by something. And then it would take the input of the microphone, add a gain to it. Yeah, so that's how you do it. Same with the MIDI buffer. Any other questions?
When you did your first audio processor example, where
Right.
did you get the same from? You had an OGG file previously, where was that?
Yes, so there I implemented my own audio processor, which I didn't show, but which I will show in the Android workshop. So that's an audio processor that I just wrote myself. Yeah. I mean, that I didn't want to show it because that audio processor could have been, let's say, a VST plugin. It could have been something closed source you don't even have access to. Does that answer your question? Or?
Yeah.
Are you running all of these examples out of the Projucer?
Yes, that's exactly. So this is all live coding. This is a modified Projucer application. And it's, yeah. Well, I mean, it didn't need much modification, but I'll talk about that at the end. Okay, any other questions? Okay, yeah.
Is the Projucer putting in the GUI components automatically as you add the parameters, or how is that?
No, that is, that's just a really bad hack. So I have some boilerplate code because the Projucer runs the live code in a different child process. It's actually quite hard to communicate between the host. So because the child process might crash all the time because I make mistakes, the slides are running in a different process than the audio. So that the audio can crash, and I don't have to worry about it. So the communication between these two needs a bit of hackery. So what it actually happens is in the child process, it constantly writes to a datagram socket, constantly writes what the current parameters are on a timer, and the slides just listen on that socket and see what parameters are available. So it wouldn't work out of the box. That's why I said a modified Projucer version. But I mean, like, modified only because I don't want this to crash all the time. Yeah. Yes?
These audio processor parameter classes, you now initialize them with a range between 0 and 1. If I take another range, how do I access the different types of values, say the value I really need for my process?
Very good question.
The value which is used to communicate to the host, because the host actually only understands 0 and 1.
Absolutely. So the question was, I sneakingly just used a range between 0 and 1. And that's sort of the, I don't know, like standard in host and DAWs, that's the normalized value. So whenever they communicate with your audio processor, they always do it in ranges between 0 and 1. And you're absolutely right. If I write there, the min value is 0 and the max value is 5, I think, okay, I have to double check this, so I'll get back to you, but I think if you read it, you still always get the normalized value. So always get it between 0 and 1. But then there's something called JMap, where you can then map that. So you can take that value, and then there's another utility function called JMap, where you can then map it to, so this JMap probes the range of the parameter and then maps that normalized value to the real range. Does that, I mean...
Is it part of the audio post?
No.
Parameter?
No, it's a separate function called, I think it's called JRange, but I'll get back to you on that. Because I'm not sure actually if you load it, I mean in JUCE we try to keep everything almost everywhere normalized parameter values. And if you don't want it normalized, you have to do the conversion on your own. And so because these classes are quite new, we might have actually done the conversion for you, but I'm not sure.
Yeah, I think it's very necessary for dB values, for frequencies and stuff like that. Right. I mean, but because when you dereference, the nice thing is that when you're dereferencing this parameter, when you're accessing the value, you already have the parameter object. So it's so easy to wrap that into another function and say 2 dB. All you do is 2 dB the parameter. And the 2 dB function can get the range of the parameter, can get the value of the parameter and do the conversion.
So it's a lot simpler as before, where you actually had to do like get parameter and index, and then because then you couldn't really pass it on to another function very easily because the other function didn't know the range of that parameter. But now, because we have these parameter objects, you can sort of pass them around, and you're always passing the value and the range, which makes it a lot simpler.
In my current plugin, I subclass AudioProcessor parameter.
Okay.
Put the logic of all this stuff inside, so then
Okay.
you can get both versions of the value.
Okay. Yeah, I'll have to check that. I mean, I know AudioProcessor parameter doesn't do any range, but I'm not sure about AudioProcessor parameter float. Does that do the necessary conversion? Because there's also AudioProcessor parameter bool, there's Pro AudioProcessor, there's many, all the different versions. So, I mean, bool must be doing some conversion. But does float actually take into account the range? I'll check that and get back to you. Any other questions? Yes?
Support for vectorized math?
Yes, so the question was, is there support for vectorized math? And there's a class called float vector operations. And it has like the most base, well, it has quite a few vectorized SIMD math operations. And on Mac and iOS, for example, we'll just call into VDSP. And on other platforms, it will do, I don't know, use whatever is available or fall back to its own SIMD code, which is like quite well optimized. And it also has FFT classes and stuff like that. Any other questions? Okay, so let's go to the exciting part. What's new in JUCE 4? So one new feature is what we call the simple play sound API, which is, well, it's kind of strange because JUCE is an audio framework, but it's really, really hard to get audio out of it. If you're writing your own audio app, actually getting the first bit of audio out is quite hard. So we fixed this problem in JUCE 4. There's this play sound API. The audio device manager now has these methods. And you can see you can just call play test sound. You can just call play sound, give it a file, and we'll just play. And it will take care of all the memory management. So for example, if you do play sound file, it has to create audio format source readers, etc. It has to buffer it, it has to create threads and all of this. But once the playback is done, it will destruct that all. Or if you quit your application before that, it will take care of this. So it's all asynchronous. So you call play sound, and it will just start playing, and the caller will just continue. You can just it won't block. You can also just play a resource. This is what I find very, very useful. So you just add your OGG, your MP3 in the introducer. You just add it as a resource, and then you just play that. Done. Another one I want to talk about is what if you want to stop the audio before, like prematurely. So you started playing, and then the user clicks on stop. So there's a play sound with a positional audio source, and a positional audio source takes another audio source, which could be like before an audio format reader, etc. And on that audio source, you can just there's a method called stop. And the nice thing about this method is if you call that and you say delete when finished, if that is true, and you call stop, it will also just tear down everything. It will delete all of the audio sources and the whole pipeline. So that's the play sound API. And then in JUCE 4, we have double precision audio floating point processing. Obviously, normally in DAWs, you do 32-bit audio processing, so you have a single precision float, but VST and VST3 support double processing, and some DAWs, not too many, also support that. So in JUCE now, we've added support for this, and all of these classes have now been adapted to double versions as well. So for example, there's this audio sample buffer. That's like the buffer class we use in JUCE. There's now a new one which is exactly identical. It's called audio buffer, but it just takes a template parameter. So it could be a double or a float. We'll get to AudioProcessor as well. AudioProcessor player now has a method that says set double processing true false. Same with AudioProcessorGraph, and a few other classes in JUCE. And if you're writing a plugin, it will be supported in VST and VST3, but also if you're hosting a VST or VST3 plugin, you can also pass on double precision data. So just as a quick, to show you how to, this is now the audio processor we wrote before. I just want to show you how we can change this audio processor so that it would support double processing. Now, here we see the process block method, which in the original version, just took an audio buffer, which was a float audio buffer, a single precision audio buffer. And if we wanted to add 64-bit support, we would have to add a double version of this. Yeah. Now, if I would do this, I would have to rewrite. I would have to like sort of copy and paste the top and rewrite everything, which is not very useful. So what I'm going to do is I'm going to call this thing process audio. I'm going to remove the MIDI buffer because I'm not using it. Take away the override. And I'm going to make this a template method. So I'm going to say template type name float type. And now I can just copy and paste float type to wherever I need it. Here, here, here. And that should be a static cast float, I believe. And I don't see any other place where it would be needed. So, and now my process block, the two versions of the process block, which is float and get rid of this parameter here, can just call the process audio. Oops. So this will just do process audio buffer. And the same thing here. Now, if I didn't do anything terribly wrong, yep, it's coming back. But the one thing we have to do now is we somehow have to tell the host that we actually support double processing now. And then there's this function that you need to overwrite, which is called supports double precision processing. What we do is we do return true. So, yeah, there you go. So, and if you look, like if you want example code for this, the JUCE plugin host now supports double precision processing. You just go into options and then do double floating point precision rendering. So you can look at the source code of that, but also the audio plugin demo now supports double precision processing. So you can just look at the source code of that. And it's basically that pattern. You just take anything that depends on the precision, you just make to a template method, and then you just add little wrappers around that. Okay, so that's from my side. Going to pass on to Timur now. Just as a quick note, this was all done in the Projucer, the live coding environment, and I think this serves as an example how, especially for when you're doing audio coding, how this live environment really, really helps, because you can like tweak the sound and you hear it immediately. So yeah, that's one of the examples of the Projucer. Any questions for this part of the talk? Yes?
Just a quick question. The audio buffer class, is there a way to create a memory-aligned audio buffer for simply access?
It is already memory aligned. So the question was, the audio buffer class, is there a way to have that memory aligned so that it's always on a SIMD alignment? So for x86, that would be every 16 bytes, right? And the answer is it already is. So every time you create an audio sample, so there are several constructors from audio sample, but if you can either take a pointer from somewhere else, then obviously you have to deal with the alignment. But if you use a constructor that allocates the buffer, then it will always allocate it aligned. Now, there's a slight problem with that is that on AVX2, the alignment has gone up from 16 to 32, but there's something in the pipeline for that. So we know about that. But I think on most processors right now, AVX2 doesn't really give you that much performance increase because internally, the microcode will just do double the old code. So it doesn't give you much, at least from my testing experience. Any other? Yes?
Can you tell us in which situations it might be useful to use double precision?
So the question was, when would it be actually useful to use a double precision? And that's, I mean, up to taste, I guess. I mean, I don't hear it definitely. Where it might be useful though is if there are any hosting applications that analyze audio plugins. So you could imagine something like analyzing the frequency response of an audio plugin. For that, it might be useful because if you do any calculations on this later on, like calculate coefficients and whatever, solve polynomials, do any DSP sort of thing, that's where it might be useful. So if you really want to probe a plugin very, very exactly.
Recursive filters.
Yes. So if you do recursive filters, so the question, so what the member of the audience just said is that if you use recursive filters, you want to use double precision, and that's true. But you would already be doing that, even if your plugin. So even if your plugin would be, presenting it to the outside world as single precision, if you were doing a recursive filter, you would already internally be doing everything double precision. So yeah. Any other questions?
Is there any possibility to have when double precision is supported, but float is not?
Well, okay, the question was, is there any possibility to have a plugin that supports double precision but not floating point precision? And if you're not the standard says no. If VST, VST3, you have to support single precision. You can support double precision. Obviously, if you're creating your own audio processor class and don't care about interoperability, don't care if it's compatibility, you can just leave the double one empty.
Yeah, but then I don't have a chance to tell or to be asked.
No, that's true. You don't have that chance to. Yes, that's true. Yeah.
Are the non-templated buffer classes deprecated now?
No, they're all, so they're now just aliases. So the question was, are the non-templated audio buffer classes, are they now gone? And they're still there, but they're just as aliases. So the real classes are the templated ones now, but they're not all templated. You have to look at the source code. So for example, AudioProcessor Player or AudioProcessor is not templated as such. There's some methods in there that are templated. The only one, I think the only class that's really templated itself is the audio sample buffer.
Okay. Hello, so I'm going to be doing the second part of this workshop and talk about a few other new features that we added to JUCE, mainly the OSC module. And then later I'm also going to give you a little preview about MPE, or multidimensional polyphonic expression. This is our extension of the MIDI standard that we're working on. So let's start with OSC. So a lot of people have been asking for OSC support in JUCE for quite some time, and so we're really happy to have added it now in JUCE 4. And it's also been a really fun new module to write, and I'm quite happy with the results, so I hope that you like it too. I'm going to quickly talk about what OSC actually is, and then the new JUCE API for that, and then also show you a little bit of demo code as well. So first of all, who knows what OSC is? Okay, so half, a bit more, so I can keep this part maybe a bit shorter, but I'm still going to go through it. So OSC means Open Sound Control, and it's a data exchange format which is sort of comparable to XML or JSON. So it allows you to transmit data, and this data is typically transmitted over the network using UDP ports. And this is a data protocol that allows controllers, apps, or instruments to communicate. And it's actually used by quite some apps and devices. And it was meant originally as a replacement or like an improved alternative to MIDI. So it has some advantages over MIDI. OSC has a higher time resolution because it supports high resolution timestamps. It supports more data types. You have ints, floats, strings, or even any kind of binary data. It has a richer parameter space. So with MIDI, you typically have this problem that you can only transmit like 7 or 14-bit integers as values. And with OSC, you can do whatever you want, basically. And it's much more flexible. And also, it's not really restricted to sound and music. You can find all kinds of other applications there, wherever you have to transmit some data between two devices or apps. The disadvantages, I would say, is that it's not quite as widely supported as MIDI, especially on the hardware side. And sometimes it feels a little bit too generic because it's really more like a generic data exchange format. For example, it doesn't even have a concept of a musical note. So there's no sort of agreement in the world how to use OSC for MIDI. It's very, very generic. So everybody's came up with their own like parameters or values to use. But it's still very, very useful. Basically, you're sending data over the network with OSC. So what you need to do, you need to have, for example, if you have some kind of app that controls something and another app which is like a synthesizer or a DAW or an instrument, for example. So these devices need to be on the same network for this to work. And then to send OSC data, you need to have a URL of your target to which you want to send the data to. And you need to use a UDP port. For example, 901 seems to be a port that several people are using. Some people are using other ports. There's no defined port that you should use. And to receive OSC, you need to know what port to listen to, basically. So that's how the network communication works. And for OSC, the elementary data structure is an OSC message. An OSC message basically is an address, which is URL-like, so it always starts with a slash, and some data. For example, here it's an OSC message with an address. It should go to some kind of fader and a number. And you can also have several data entries. For example, if you want to transmit like the parameters for an equalizer, for example, you have frequency, gain, and Q, you would have 3 numbers in one message. So that's also possible. And we call these contents of a OSC message the arguments, or the OSC arguments. OSC supports 4 data types: integers, floats, strings, and binary blobs. There are some extensions to support more, but plain OSC supports these 4. And you can also mix them. You can have one OSC message which has an address and then several data entries of different types. That's also not a problem. And also, the OSC specification says that there should be a certain binary representation of this data. There's some bit padding and all this kind of stuff. But if you're using JUCE for OSC, don't worry, JUCE will take care of all the low-level binary representation. You don't have to worry about it. So OSC messages. And then on the receiver end, you have something that's called an OSC method, which is basically something that also has an address. So it expects messages that have this address, and then it invokes some behavior when it gets a message. So that's the most basic OSC receiver has an address and invokes some behavior when it gets a message. And because these addresses are URL-like, what you can do in your app is you can build this kind of tree, which is called an OSC address space, where basically you structure your app hierarchically and you have these addresses to build like an address tree. And this way you can route the messages to certain parts of the app. For example, your EQ can be one part of your app, and then it has some parameters in there that, or some behavior in there that's invoked by OSC messages. And you can have other parts of your app which use other suffixes. So you can build trees like that, but you don't have to. You can just use plain OSC addresses for your methods. And yeah, that's the basic way how OSC works. You have a message which is then sent over the network, and then you have a method that has the same address and invokes some behavior when it gets this message. So let me just quickly demonstrate that to you. Oh, sorry. Okay, I have a problem with the screens here. So I have to stare at that screen for a second. Bear with me. Oh, maybe I can do it like this. So in JUCE, here we have this examples folder, and here there's a few new OSC demos here. So we have an OSC sender. I'm just going to open that and run it. So that's just basically a knob. And then there's an OSC receiver, which is the same knob, except you can't turn it, it just receives. And if you put them side by side, oh, where's the other one? Yeah. So you see if I turn one, then the other follows, and this one is transmitting OSC messages to the other one. And this is now runs on one machine, but since it's over the network, you can also do this, have different devices communicate with each other. For example, I have put the same app here on my phone just before the talk. I just hope this works because the Wi-Fi here is not quite, yeah. So here, I have the same knob here, and if I turn this, then that one turns, and this is communicating over the Wi-Fi here. And you can imagine, so this is like a really simple demo app with one knob. It's basically one float number here that's transmitted. But you can imagine that in this way you can build, for example, a whole control surface with all kinds of knobs and faders and everything. And then on the other side you can have like a synth or a DAW, and then you can control it with that control surface. That's, for example, one application of OSC. There are many others. So there's many interesting, creative things you can do with it. All right, let me go back to my presentation. OK, so there's a few other things that OSC allows you to do. For example, OSC has pattern matching. So what you can do is, on the message side of things, you can use a wildcard expression, like an asterisk there. And then this message will match several addresses. For example, you can have fader 1, 2, and 3. And then if you have a message with a wildcard expression fader star, then this message will go to all these 3 faders. This is called an address pattern. So an OSC message has an address pattern. And OSC allows a certain set of patterns, which is a certain subset of regex. It's not all of regex, it's just a certain subset of it, that the OSC specification specifies what this should be. So we implemented this in JUCE as the OSC specification says it should be. So basically you have a question mark to match a single character, you have an asterisk to match 0 or more any characters. You can use the square brackets for a set of characters or range of characters. You can negate it with an exclamation mark. You can use the curly brackets to match substrings, and you can also combine them in one expression. So you can build complex patterns in your messages, and then you can have on the other side receivers that match them. So and it's all dispatched. OK, so there's one more thing we're almost done with what OSC is. There's one more thing in OSC, which is called a bundle, which adds the notion of time. So you can have a bundle, and the bundle always has a high resolution time tag. It has like sub-nanosecond resolution, so it's really enough for all your musical needs. And so you have a time tag and then some content. And in such a bundle, you can put several messages with this time tag, and then the semantics is that basically these messages should then be invoked simultaneously at that time. And if the time is 0 or in the past, then this means immediately. And one last thing that OSC allows you to do is you can actually nest bundles. So you can have a bundle within a bundle. And to be honest, I haven't seen a useful use case of that so far. But it's in the specification of OSC, so we implemented it in JUCE. It all works. It's all supported. If you know a good use case for it, go ahead. JUCE can do it. And so the contents of a bundle are called bundle elements. So OSC bundle elements can be either messages or other bundles. So that's OSC, basically. Yeah, any questions about that? Yeah.
Is there any way to query the parameters that a receiver is expecting? Is there any way to get those messages? Can you ask what is supported? You've got the receiver that's receiving JUCE foo, and you've got something sending to that. Is there any way that the sender can say, OK, give me all your parameters and what you're expecting?
I think we're going to see this later in the demo code. Maybe it's going to be a bit easier. So basically, if you get a message that matches your address, you can take it apart and see what's inside, and then decide what to do. We will see some code later. There's another question there? Oh, sorry. Yeah.
You're supporting 1.0. What about 1.1 and some of the extra data types that are in that?
So the question was, we support 1.0, what about 1.1? So OSC 1.1 offers some extensions to 1.0, which are not in JUCE at the moment. But this could be an interesting thing to add. So we don't have 1.1 at the moment.
And are you planning, or do you have any sort of service discovery mechanism?
Sorry, I didn't quite hear that.
Do you have some sort of service discovery mechanism to be able to find out what's running on what port where?
The question was if we have a service discovery mechanism. You mean like on the network?
Yep.
Not in the OSC module, but since it's all running on basically datagram sockets, network sockets, I think it could be easily implemented.
Yeah.
I was just wondering if you were planning some sort of standard-ish way of doing that.
We could add this in the OSC module maybe. Let's talk about this later. It's an interesting idea.
Sure.
Little question.
Yes.
It wasn't mentioned, but I believe any receiver can be a sender.
Sorry, can you repeat the question, please?
Any receiver can be a sender.
Any receiver can be a sender. Whether that's the case, is that the question?
Is it possible to have one unit both?
So these are, OSC sender and receiver are different entities, but if you're in the code, you can have a class that derives from both and does both sending and receiving. It's really easy to put this together. So it can be done, yes. All right, so that's OSC. Let me talk a little bit about the JUCE implementation. So we have a new module which is called JUCE OSC. It's now included in JUCE 4, so you all have it on your flash drives and your attendee bags. It's a complete implementation of the OSC standard. It's a really clean and easy to use API that's fully documented just as the rest of JUCE, and it integrates also very nicely into the rest of JUCE. And we have some example apps in there as well. So what do you have to do to add OSC support to your app? You go to the Projucer, you right-click on the modules, and you just add the OSC module. And then you resave your project, open it in your IDE, for example, Xcode, and then you get all these new classes over there. So for the rest of this OSC workshop, I'm just going to quickly go through the API and how to use it. So let's say you want to send OSC. So there is a class in JUCE that's called OSC sender. So basically you just create it and then connect. And you have to tell it the URL of the other end you want to send it to and the port you want to use. That's it. And also this connect method returns bool, so it can tell you if it failed, and then you can handle that by returning something or throwing an exception, displaying an error message. And so you have an OSC sender, it's connected to the network. You want to send an OSC message, so there's a really simple method which is just called sender.send. And then the first .send, the OSC address, and then the following arguments are the contents of the OSC message. So this is a message that just contains one float, but you can also add more because an OSC message can have an arbitrary number of arguments. So you give it the address and then a list of arbitrary parameters, which can be ints, strings, or floats. And also OSC offers you binary data. It's called blobs in OSC. So how do you send a blob? Well, a blob in JUCE is just a memory block. So you create a memory block. It's a JUCE class. It's been there for a while, and you just send that. No problem. You're sending binary data over OSC. Really simple. And the send method also returns true or false, so you can check if that failed. Yeah, and that's it, and it's really, really simple. Let me just show you how it works in the OSC sender demo app. I may even have it open still. Yeah, here it is. So here I have this knob that you saw earlier. It's just a slider, and then there's a callback if the user rotates the slider, and then if the slider has changed, you see what value does it have. And then, there was an OSC sender here, which is also just a member, and I connect it here in the constructor. And yeah, I just send the message. It's just really 2 lines of code. And actually, you can even simplify that. You can just put that here. And that's everything you need to do. 2 lines of code, you're sending OSC. Really easy. All right. So, but what if you want to do more with these OSC messages? So this is sort of like the shorthand syntax, which is really easy. But if you have a little bit more of a complex app, then you can also create these OSC messages and send them later. That's also not a problem. There's a class called OSC message. It's used in the same way as you saw earlier. You give it the address as the first argument and then an arbitrary list of all the other arguments. And then you can store it, and then you can send it later by doing send message. And And then there's also a little bit more explicit syntax where you can actually create the message and then add the arguments one by one. Maybe you want to do that. That's also not a problem. And actually, the functions that you saw earlier, they're using variadic templates, C++11 variadic templates. So if you don't have C++11, anybody here uses C++98? No one? OK, that's good news. But if you do, you have to use this version because you don't have variadic templates, right? Yeah, and then also we have full support for the OSC expressions and pattern matching. So how you do this, you just create a message, and in the address you just add your expression. And it's all passed internally, and you don't have to worry about it. Just write it, and it will work. You can also, OSC message has a few other helper methods that you can use. You can give it an address, and then if you change your mind, you can give it another address later. You can query the address. Oh, it's actually called address pattern because it can have wildcards. You can query the address, you can print it, you can do whatever you want. That's the complete API of the OSC message class. I just removed all the documentation so it fits on the slide. So it has this constructor, it has this variadic constructor where you can give it the arguments. You can set and get the address pattern, you can ask it how many arguments it has, you can ask if it's empty. And then there are these ones here. Oh, and also there's the clear, you empty the content. And these ones here are interesting. They allow you to iterate over the message and iterate over the arguments, over the content. And these return pointers to an OSC argument. And this is because the contents of the message can be either ints or floats or strings or memory blocks, you don't know. So you need some kind of wrapper for type erasure. And this is what the OSC argument is. It's more or less like JUCE var, if you're familiar with that. It's like a type erasing wrapper around, or like boost variant. It's doing the same thing. It's just a wrapper around the 4 types that OSC supports: int, string, float, and memory block. And it's also possible to add more in the future as well. So if you're iterating over a message, you get pointers to these, and then you can ask them what type they are, and then get the value, basically. Be careful here. If it's an int, but you're asking it to give you a blob, but it's not a blob, then it's going to throw an exception. OK, so that's that. One more missing thing are the bundles, which we also, of course, support. I imagine most people won't use bundles if you don't have like some kind of timeline or something, but it's all there. So you just create a bundle by doing OSC bundle. You can add messages to it. You can also add other bundles to it. So you can either create the messages like that and then just do add element, and then you can just send the bundle and you're done. Or you can also add the elements in line. That's also not a problem. So that's all you need to do to send the bundle over OSC. And bundles have these high-resolution time tags. So you can, if you don't do anything, it's going to have a time tag, implicit time tag of immediately. It's like a special value. But you can also explicitly add a time tag. For example, if you're working with some kind of maybe DAW with a timeline, you would probably say, OK, it should be now, but then 400 milliseconds later, for example, or like a couple of bars later. Or, yes?
Are messages guaranteed to be received in the order they're sent?
Yes. Let me think about this for a minute. Yes. I mean, they're sent. So if you send a bundle, then it's going to iterate over it. It's going to convert it to binary and send it in the order you. Yeah. So yes. So yeah, you can add a time tag explicitly to a bundle. And so we have this OSC time tag type, which is the way OSC does time tags, but we also did it in such a way that it implicitly converts to and from a JUCE time. So if you know JUCE, there's JUCE time class, you can just use that. So you can either construct a time tag from a JUCE time, like this, for example, and then set the time tag, or you can construct the OSC time tag directly from a JUCE time, or you can do it all in one line and just construct the bundle, and it takes an optional constructor argument, which is the time tag, and you can just use a JUCE time there. Very simple. So here's the API of the OSC bundle class. It's also, I think, quite clean. So you have these constructors. You can set and get the time tag. You can also ask for its size, whether it's empty. You can add an element, which can be either a message or a bundle. And then also you can iterate over the content with the begin and end. And there's this operator here. And the contents are elements. And this is another wrapper similar to the one that you saw earlier that can be either a bundle or a message. You have to ask what it is, and then you can get the content. So that's that. That's everything you need to know to send OSC. And yeah, on the other side, you want to receive OSC. And this is also really simple. You create an OSC receiver. It's also a new class in the JUCE OSC module. You create a new OSCeiver object. You connect it to a network port. And then you can add a listener to it. And then that listener will receive callbacks when OSC is received. And here's an example. For example, you have a synth that wants OSC data. So you derive the synth from OSC receiver listener. That's that. And then you have two callbacks that you can implement. It's OSC message received, which will be called if you just receive a plain OSC message. So you have to implement that. And then there's an optional one, OSC bundle received, which will be called if you receive bundles. Some people are not interested in bundles, so this one is optional. It has a default implementation that's empty, so you can just skip it. You're not interested in bundles, no problem. So that's that. And there is this additional template argument here, and I'll talk a little bit more about this because this is interesting. So this thing can have two different values. It can be either a real-time callback or a message loop callback. So you have this option. If you do a listener, which is a real-time callback, then you will get the OSC callbacks directly on the network thread where the OSC data is received. So it's very low latency, and it's really good to do things that don't require much work, but they have to be fast. For example, you have an audio app and you want to update some kind of real-time parameter. Then it's just setting a few values, but it has to be quick. You can use the real-time callback. Of course, if you have an audio thread using that, you have to synchronize the thread properly. If you want to know more about that, I'm going to do a little talk tomorrow about this topic. And the alternative is the message loop callback, where you get the callbacks on the message loop. So this is obviously slower, has more latency, but then you're on the message thread, so you can do more work there. For example, you can, if you have like a GUI that has to update, you can do that there. That's typically, the first one would be for some kind of real-time parameter thing, and the second one would be if you want to update your GUI or render something or do something that doesn't have to be that fast, but involves more work. So one more thing I should say is that this kind of listener receives all the OSC traffic. So if you add a listener like this, and you have an OSC receiver, then you get all the incoming OSC will end up in those callbacks. And then here you get a reference to the message received, and you can take it apart, iterate through it, and do whatever you want. But there is also another type of OSC callback in JUCE, which is the listener with OSC address. And this one implements the pattern matching thing. So, for example, if you have several elements in your app and they all should just react to OSC messages with a certain address, then you should use this class. And this is very similar, except that if you add this as a listener, you have to specify your address that you're going to be listening to. And then under the hood, there is a parser, there's a pattern matcher. It was very fun to write, by the way. That does the OSC pattern matching and dispatches the messages correctly to the listeners that match that address, and it's all going on under the hood. You don't have to worry about it. It just works. And then you get this callback here. There's no callback for bundles because bundles don't have an address. There's just a callback for messages, and if you end up in this callback, you know this is a callback. This is a message which matches your address. And then you can go ahead and look what's inside and then invoke the behavior that you want to do. So just to reiterate this, there is this listener, OSC receiver listener, which listens to all OSC traffic and receives all OSC messages or bundles. Bundles are optional. And then there's the listener with OSC address, which just receives the messages which match the address you used to register that listener. And they both have this callback type template parameter, which can have these two options, real-time or message loop. So that's how you receive OSC. I can just quickly show you how this works in practice. So we have two demo apps here. There's the OSC receiver. And So what I'm doing here is I'm actually deriving from it. That's also an option. You can have it as a member, or you can also derive from it. And because this is a really simple class, also here, this class is its own listener. You don't have to do it like that, but it's a quick way if you really have a very small class. And then this also has the same slider here, and then that's the callback. If the OC message is received, you check its size, and if it has one element and that element, one argument, and that argument is a float, you set the knob to the value of that float, and you're done. And that's how you receive OSC. Any questions about that? Yes?
I have two small questions. One is there any way to reply to the sender of a message?
Is there any way to reply to the sender with a message?
So you receive, like, from your listener, you receive a message. Can you know, let's say, from which IP address it was sent from?
Well, you know its address. You know its OSC address. You don't know which IP address it came from. You don't know.
Okay.
But you can send the messages in such a way that they have a certain address, for example, or a certain content, and then you know that's the content you're expecting.
Okay. Okay, and the second question was about the bundle. So you have a separate method for bundle received.
Yes.
So does it mean when you receive a bundle, it won't be decoded as messages, it will be just a bundle. So if you don't implement the bundle received, you will not processing any message.
Oh, no, it's not quite like that. So with OSC, we can send either plain messages, you can just send messages, or you can send messages which are wrapped in a bundle. And these are two different things.
Yeah.
And so basically, this callback will only receive the messages that are not wrapped in a bundle, that are just sent plain, and this one will receive all the bundles. So all the OSC traffic will end up either in this callback or in that callback.
Okay.
Does that answer your question?
Yeah, it answers my question, but I find it a little bit odd because I think in many cases, from the library I've used, they all get decoded as messages, even if they are bundles. So if you just listen to messages, whether they are message or bundles, you receive messages.
Well, the bundles also have the time tag, and bundles can have other bundles inside them and this kind of thing. So it involves a little bit more parsing to take the bundle apart on the receiver side. So it's implemented separately.
Yeah.
So if you, for example, if you receive a C message, then this probably would be, it involves less code under the hood, right?
No, I understand. You just expect, then you require the sender to be sure that they are sending messages or bundles. So, you need some control over what sends the sender.
Well, you need to know whether you expect plain messages or bundles.
Exactly. No, I understand.
But with a couple lines of code, for example, what you could do is if you receive a bundle, you can just iterate over the bundle, and all the messages inside, you can just call that one again, and then implement all your logic here. Okay. So it's just a couple lines of code to do what you want.
Oh, true. Okay. Clear. Thanks.
Okay. Yeah, that's actually everything on the OSC module. So if there are any other questions about OSC, yes?
Is there a limit to the size of the message? The size of the message, is it limited or unlimited? Can I send audios?
There's nothing about this in the OSC specification. And yeah, no, there isn't. Because there is a certain size of packet that you can send over UDP, but the receiver will wait. So if it receives like an incomplete message, then it will just wait for the next packet, and then it will invoke the callback. So there's no implicit limit in JUCE.
Since you mentioned UDP, UDP does not preserve order. And you said before that the order of the messages will come in the right order. So.
He said that he sent in the right order.
I was asking how they received
Oh, right.
Okay, that's an interesting question. Let's discuss this after the talk. Okay, cool. If there are no more questions about OSC?
I've got another question.
Yeah.
Is there a way where I can ask the network for all its listeners, current listeners?
Is there?
I'm trying to create some communication protocol between a controller and, say, a host.
Yes.
and I would like the controller to display all kind of meters for the current state. Suppose in your sample, I would require that the client will show the exact state of the receiver.
So what do you mean by client?
This will assure that the client is in the exact state as the server, say, the receiver. So I should have some protocol between the two of them, between the client which controls the other slider.
Okay.
So
you can
client should also be a receiver.
Well, you can listen to multiple. So you're listening to a port, so you can get messages from multiple instances. I think that's a little bit more of a complex question. Can we defer this until after the workshop?
An UDP connection.
Sorry?
That's not an HTTP connection, so I can't listen. It's an UDP. So
you can listen to a port, and then you get all the network traffic on that port, and then whatever is OSC will end up in the callbacks. Okay, one more question here.
When you were showing the example with your phone,
yes.
How did you know what IP address to send the messages to?
Oh, I cheated a little bit because I have to put in an IP. So I basically just before the talk I looked up the IP of my Mac and I compiled it with that.
No DNS or any kind of.
It's got to be well, IP. You can use broadcast. You can send it over a broadcast IP, and then everyone in that subnetwork will get it.
And JUCE supports that.
Yeah, JUCE supports that. That's actually not even in the OSC module. The OSC module under the hood uses the datagram socket class, which is another JUCE class, the networking JUCE class, and it supports all of that. Actually, I can show you like how you would do this in practice. There's a third demo app here, which is an OSC monitor, and you can see here it's this other kind of listener which gets all the traffic, and here you can actually specify the port number you want to listen to, and obviously from the sender side you can also, I think typically like controller OSC apps like TouchOSC, for example, they have it somewhere in their preferences that you can specify the IP and the port. You can obviously do this with JUCE. And if I just try this again, if the network still works, okay, so this is something with the Wi-Fi here, but so it would. Okay, I don't know what that is, but it would show you all the incoming OSC. Sorry? Oh yeah, you're right. I have another application using that port, so I should better close that. Thank you very much. Yep. And now if I just do this again, see, I have some incoming OSC messages here. Okay, so that's it about OSC.
We've got one more question down here.
Okay.
Yeah, is there any provision for authentication? Like if you're running it on an open network and you don't want just anyone connecting to it or want to control access to it?
This is something outside of the OSC module. This is more about the networking stuff in JUCE. Fabian, do you know something about this?
The simple solution would be to use a VPN or something, and then route the UDP over that. But I don't know. Does anybody in practice know of a way to authenticate UDP or OSC? Well, if you encrypt the message,
Okay. So let me get to the final part of this workshop, which is to give you a short preview of MPE. Sorry, hang on. Okay. So that is equator. That's the synth that we do at Rolly. And here's the rise, and we should get some sound. So you can check this out, the rise and equator. I think we have some of them standing around here. So what's happening here is that you have a really expressive instrument, and you can, for example, bend a note like this. You have pitch bend, you have that axis, and you have also pressure. And you have all that polyphonically. So you can do this with 10 fingers or even more, and every note will have this polyphonic multidimensional expression. So how do we do this? Because at its heart, the rise is actually a MIDI controller. So we need a way to transmit this multidimensional per note expression over MIDI to the software. And this is something that we call MPE. I'm just going to give you a quick tour of that because it's not released yet. So I hope that we can do a more in-depth presentation of this at some point. But here I'm just going to keep it really short. So MPE stands for Multidimensional Polyphonic Expression. It's a new industry standard, and it's an extension of the MIDI standard. And there's a preliminary spec available here. It's not yet approved by the MMA, which is the governing body for the MIDI standard, but it's a work in progress. And we have it in JUCE, and it will be available to everybody at some, hopefully soon, point in the future. So this standard, we at Rolly, we are spearheading this development, but there's many other companies behind it. So this is the group of companies that are working on this in no particular order. And MPE is a protocol that we support at Rolly. We support it in JUCE, we support it in our equator synths, and we also support it with our C-board instruments. But it's not restricted to that. So there's many other expressive controllers that support MPE to some degree, which is, for example, the Eigenharp, the Linstrument, and the Haken Continuum. Maybe some of you have heard about that. So these are all expressive instruments that go beyond, for example, what piano keys offer you and give you per note expression in various ways. And also there's several DAWs that support it. So Logic has released a version in August that brings MPE support. Bitwig is going to add MPE support soon, as far as I know. And then also Cubase supports multi-channel MIDI via their note expression technology. And with that, you can get MPE to work as well. So it's really the set of people and companies and DAWs and instruments supporting this is growing because it offers you all these extra dimensions of polyphonic control, and you can actually use MIDI to transmit them. Here in equator and in the rise, we have these 5 dimensions, which is basically strike, that's the note on. Then you have the press. If you press it, it controls the volume, for example. You can map it to any other parameter. Then you have glide, which is, for example, the pitch bend. You have slide, which is that dimension, which you can assign to some kind of filter cutoff or timbre or anything you like. And then you have lift, which is the note off. So how do we transmit all these dimensions per note? So MPE basically is a way or an extension of MIDI that tells you how to transmit these dimensions per note using the existing MIDI standard. And so at the very basic level, there are 5 dimensions, which are called strike, press, slide, glide, and lift if you're an equator user. In the MPE standard, and actually also in JUCE, we call them note on velocity, pressure, pitch bend, and timbre. Timbre can be anything that's not pressure and pitch bend, basically, and the note off velocity. And then MPE tells you that there are certain MIDI message types that you should use to transmit them. And the big challenge is, in MIDI you have 16 channels. So how do you utilize these? Because you can be playing many notes at the same time and modulating them in all these dimensions independently from each other. So basically MPE you can look at it as a really clever way to utilize the existing MIDI channels to convey that per note information. So basically it maps notes that you're playing to certain MIDI channels and then transmits the messages on the right channel. It's a bit more complicated than that under the hood, but that's the basic idea. So we can have an MPE zone where we can have a master channel and the rest are node channels. And on the master channel, for example, you can transmit some kind of a master pitch band or other parameters that should affect the whole instrument. And on the per node channels, you have all these, you can do like per node pitch band, per node timbre, per node pressure data. And MPE sort of is a clever way to dynamically assign different MIDI channels to different nodes that you're playing and making sure that all the messages are arriving correctly. And there's lots of funny edge cases, like if you bend a note and then you have a master pitch bend, then you should add them up, and then you can have different pitch bend ranges maybe that you should treat properly. Or sustain pedal is also one of my favorite edge cases. Really weird things happen if you have sustained notes on channels, and then maybe you have notes that are received on the same channel, stuff like that. So MPE is a way to deal with all that complexity. And one feature that we recently added is that you can also have multiple MPE zones, which can be anywhere in this MIDI channel parameter space. So you keep utilizing standard MIDI messages, but you have a clever way of interpreting them to convey all that polyphonic expression data. So for example, you can have 2 zones. It's really useful. Maybe you have an instrument that has a split keyboard maybe, yeah? And then, or 2 keyboards or 2 other areas where you can do something. And this kind of stuff. So this is really basically for people who build interesting expressive instruments or synths or software, to give them a way to communicate this additional expression data using standard MIDI. And we've added this in JUCE. It's not released yet because we're still working on some details. For example, what we want is for you to use this technology. Maybe you have a synth that's using the JUCE synthesizer class. So what we would like is a situation where it's really easy for you to migrate to something new without much changes to your audio plugin, for example, and then you just get that MPE functionality. And also you keep supporting the old standard MIDI as well. So we're sort of still working on ways of how to make this simpler for you. But the MPE functionality itself is already there. It's already in JUCE. We use it in Equator and other places. I can just give you a quick demo here. So, for example, here's hang on. So here's a little MPE test application, which is unfortunately cropped because the projector has only a limited resolution. Sorry for that. But yeah, you can define your channel layout. You can define the pitch bend ranges you want to use. You have MIDI input and output. Actually, it also works the other way around. If I add a zone, then it also sends MIDI messages to the rise. So to set up this layout, there is also a specification like they should use certain RPN MIDI messages. And it's also all built into JUCE, so you don't even have to worry about that. And if I play now, I'm not sure if you can see this because of the contrast here, but basically this is a test app for people who, for example, build devices that should be MPE compliant. And you can see here, this number is the MIDI channel that the node is sent on, and then you can modulate here the pressure, you have the timbre axis, you can bend it, and you can do all that polyphonically. And I know the sound is horrible, it's a square wave, and I'm just modulating the pulse width because it was quick to implement that. But yeah, you can build all kinds of creative, really creative, innovative things with it, both on the software and synth side and on the device side. And so we hope to release it soon in JUCE, so you can actually all benefit from this, all this technology. So just watch out for news and updates on that. Yes?
There are currently, you have written there 15 number of node channels.
Yes.
15. So it is, you cannot have more because there are only 16 MIDI channels. So
correct.
What about synths which have more voices, like 32 voices? If you have a pad sound and you want to play chords, and then you can easily get beyond 15 voices.
So it doesn't mean that you can only have 15 notes at the same time. It doesn't mean that. So if you have 15 fingers and you press 15 notes,
okay,
and then you have a 16th finger and you press a 16th note, then that note will be assigned to a channel, for example, the same one as the oldest one. So you will have 2 notes on the same channel. And then there's options in MPE, which note should be the one that you're modulating. Should it be the last one that was played? Should it be maybe the lowest one, the highest one? Should it be both? And these are all options that JUCE offers as well, so you can tweak it.
Okay, but you cannot really modulate the 16 notes independently.
What you can't do is you can't modulate more than 15 notes independently in all of these dimensions.
Okay.
So you can have 100 notes at the same time, but you can only modulate, like multidimensionally modulate only 15 of them if you use one MIDI port.
Okay,
yes.
Thank you.
But this is a limitation. Basically, it's a trade-off. We could have gone for a completely different protocol. We could have used OSC or something else. And this is sort of a trade-off, because you can say, okay, we want to support this, what you just said, but then we can't use MIDI. Or we find a clever way to basically exploit the existing MIDI standard to the highest possible degree, and then we have to live with limitations like that, but then we're using MIDI. So, and then it's easier to be compatible with everything else. So that's sort of a trade-off that we made, yeah. Okay, cool. So that's the audio workshop.